Okay, so we have introduced new quantities while talking about the spontaneity of reactions. For example, we talked about Helmholtz free energy A as U minus T s and Gibbs free energy G as H minus T s, and also also H enthalpy as U plus P v. We talked about enthalpy before, but in the context of spontaneity we talked about enthalpy in the last lecture. Now, we are going to tell you that these different things like enthalpy, Helmholtz free energy, Gibbs free energy, they are not some quantities just for spontaneity itself. They have a deeper connections with the thermodynamics, because they are all thermodynamic potentials. So, how do you understand that? So, in order to understand why they are thermodynamic potentials and why they are important, because again if they are criteria for spontaneity, means of course, they have some role to play in determining the change of matter, which direction it will go and all. So, we are going to we are going to show you that how these quantities arrive, and that is typically known as Legendre transformation. So, the reason that Legendre transformation is important, or it came up, because if you look at the fundamental equation, so fundamental equation in U depends on S, V and N. In fundamental equation of U, which is called energy fundamental equation, there is also corresponding entropy fundamental equation, where S is a function of U, V and N. So, if you see the fundamental equation, U depends on S, V and N, all are extensive variables, and it is not always easy to measure the extensive variables. Often we want to have quantities parameters that depends on intensive variables like temperature, pressure and things like that, and because they are easy to measure in experiment. So, therefore, it would be good to have a function that depends on intensive variables. However, you know that if we do that, if we take the derivative of the function, for example, if I take du by ds as you saw earlier at a constant V and N, it will give you the intensive variable temperature. Now, in that case we are losing information. I can give you an example of a one dimensional function. Let us say y depends on x, and let us say this is the function that we are talking about, and you know the derivative of the function, which means slope, I can obtain at any point by let us say calculating slope of the function p, which is let us say defined by dy by dx. So, if you see this particular function slope, then this p is not really an unique quantity, because p can be obtained. So, p is a unique quantity, but it can be obtained from multiple values of y. For example, if y is expressed as y plus c, or let us say y plus c. So, let us say a function of another function of y 1 x depends on y x plus c. In that case, del y 1 by del x is same as del y by del x. So, p will be same in the cases of so many different functions which are created by adding some constant value. So, therefore, p will be same for a series of functions. So, now if I draw a series of function like this, which are all like parallel and shifted by c, then all of them will give the same p. So, therefore, whenever we take the derivative we are no longer going to get the same fundamental equation, because remember the fundamental equation has all the information. However, derivative of the fundamental equation, which we call as equation of state, that does not have all the information, because we are projecting onto a particular lesser dimension. For example, what I mentioned here, that many functions will give the same value of p at that. So, therefore, the concept of Legendre transformation is that you want to keep the same information. However, you want to express same information that is there in the function y x by something else. So, for example, so let us say this is my y and this is my x, and all the different points represent for a given value of x a particular value of y, or all possible values of x and y is our particular graph, and in that this graph represent that for a given value of x, what is the value of y, for a given value of x what is the value of y, for a given value of x what is the value of y. So, for every value of x there is a particular value of y, and that is what the graph is, and this graph let us say contains information about the system of thermodynamic system. So, in that case, if I just take the slope, as you see that it will not be possible to exactly determine the all the information about the system. However, let us say instead of slope, if we also calculate one more quantity, and that is intercept of the function. So, in that case this particular point x y, let us say I call it x y 1 x 1 y 1, will give a particular value of p 1 slope and a particular value of intercept, let us call it psi 1. So, every point x y 1 y 1 on the graph will correspond to a particular point, let us say this point is x 2 y 2, will give us a particular point of p 2 and psi 2. So, therefore, we can map a function x y to psi p, and that is what the Legendre transformation is. So, given a graph x y, where for every value of x we have some value of y, we can always have all the informations contained in the graph be represented by another pair of points psi and p. So, for every value of this thing we will get that, and therefore, we are not compromising on any information. As soon as we put the psi, it will be no longer same as for all possible parallel lines, because as you can see in this particular case, if I have a slope here, it will have a particular intercept, and this slope will have a different intercept. So, if we talk about only slope, they may be similar, but intercepts will be different for these parallel lines. Therefore, keeping both the slope and the intercept, we are going to map the complete information from x y point to a psi p point. And as you know, the p, as I have discussed, that p is an intensive variable now, because it comes as a derivative, and psi is now a function of that intensive variable p. So, therefore, we can represent a thermodynamic function y x, where x is an extensive variable, to be cast into another function where that function is a function of intensive variable. So, this is intensive and this is extensive, and reason is just that we want to express a function in terms of intensive variable for our convenience, because it is convenient to measure temperature. You know that, right? Several ways to measure temperature, but there is no way to measure the entropy of a system. So, therefore, if you cannot measure the entropy of a system, we cannot get the value of u. But if we cast the same information into something else where we can measure temperature and get the information about that, then we get the information about the thermodynamic system much more easily. So, that is the reason of converting this one set of pairs of points to another set of pairs of points. Now, how do we do that? It is actually extremely very simple. So, for example, we know the definition of p. P is a slope. Slope means the difference in y. I am talking about 2 points. One point is x y on the graph, and another point is 0 and psi. because as you know psi is the intercept, right. So, intercept meaning the value of y at x equal to 0. So, value of y, so this is also x y points, but value of y at x equal to 0 is nothing but psi, because that is the intercept of the function. So, this is, let us say for example, this is the value of y at value of x equal to 0. So, therefore, I am taking 2 points, one point is this particular point and another point is any of the points that is mentioned here x y. So, then I am talking about slope is nothing but dy by dx, which is delta y by delta x. So, I am talking about the difference between y minus 0 divided by y minus psi divided by x minus 0. So, that is the definition of slope. So, then automatically what we get is x p is y minus psi, and what we get from there is psi is y minus x p, which is, if I write it little bit in a nicer way, p is nothing but slope of the function. So, del y by del x into x. So, this is for one dimensional function. So, you can see that for multi-dimensional function, let us say if it depends on more than one variable, let us say our y depends on more than one variable, then we have to use a subscript for that. So, that we can talk about only slope in one particular variable. We are going to show you immediately right now. So, this is what the Legendre transformation is. This is what called Legendre transformation. So, you see that by doing the Legendre transformation, we have not compromised anything, we have got all the informations. At the same time, we have cast our function which was dependent on extensive variable to now a function which depends on intensive variable. Now, we will do that and we will show you that how we can get that. So, let us talk about our y, which was a function of x, as u as a function of s, v and n. So, this is our thermodynamic fundamental equation, right. So, now we are going to write a function psi, which is u minus derivative of u with respect to x. So, del u by del s, and since it depends on multiple variables, I said that we have to use the other variables as constant, and then we have to just multiply with s. And you know what is du by ds at a constant v and n, right, that is nothing but t. So, u minus ts, and u minus ts we already defined as A. So, you see we got Helmholtz free energy just by we name it as Helmholtz free energy, but this A is nothing but Legendre transformation of u. Now, you know that we are going from y x to psi p, p is the slope. So, here this is the slope, right. So, therefore, it will depend on t, and since we have not changed the variable v, it will depend on v and n. So, now A depends on t, v and n. So, since u was a thermodynamic potential, A is also a thermodynamic potential. So, let us now do another Legendre transformation which is a different variable. Now, we do u minus, now we are going to do with respect to v. So, del u by del v at a constant s and n v, and what does that give us? U, now minus du by dv you know is plus, right, plus p, u plus pv, and we have defined earlier, named it as h, and what does it depend on? It will depend on the slope, which is p, and rest of the variables will be constant, which is s and n. So, h is a function of s and n, and we call that as enthalpy. Now, we are going to do one more, psi as both the variables. So, we do now Legendre transformation on both the variables. So, del u by del s at a constant v and n s minus del u by del v at a constant s and n v, which gives us u minus T s minus plus P v, and u plus P v is h minus T s, and that is nothing but g, and it will depend on which are the slopes, T and P. So, T and P, and n was not changed. So, n is also there. So, this is called Gibbs free energy, or we name it as Gibbs free energy. So, now you see that from one fundamental equation where u is function of extensive variables, we have arrived at 3 new fundamental equations and 3 new thermodynamic potentials, where now the variables got changed to from extensive variable to intensive variable. For example, you can see G is function of 2 intensive variables and H here is function of 1 intensive variable, because only one we changed, and Helmholtz free energy is function of 1 intensive variable, because one only we changed, but G is function of 2 intensive variables, only one extensive variable, that is N. So, you see now we call this particular thermodynamic potentials like A, H and G are nothing but avatar of the same God, because it only appears that they are there with a different appearance, however, with the same identity. Underlying information contained in this particular thermodynamic potentials is always same, whether or not we write them in a different way. So, once we get that, now we will summarize again our all thermodynamic potentials. So, u is a function of S, V and N, and we have seen that du as del u by del S V N ds plus del u by del V S N dV, and we are not talking about N now. So, that is T ds minus P dV. Okay. So, now H is a function of S, P and N, and therefore, you can write dH as del H by del S P N ds plus del H by del P S and N dP, which is del H by del S as constant P and N is nothing but T ds, and del H by del P is V. So, T ds plus V dP, right. So, we also know that, because you know H is equal to u plus P V. So, del H is del u plus P dV plus V dP, and du plus as you know that du equal to dq plus dw, which is T ds minus P dV. So, therefore, du plus P dV is nothing but T ds plus V dP, and that is what we got here, and we know that del H by del S is T and del H by del P is V. Similarly, we got A as T, V and N, which we expand as dA del A by del T at a constant V n dt plus del A by del V at a constant T n dV. Remember, we are not doing the n part, but otherwise it is fine. Now, what is this quantity? In order to understand that, we have to expand that as u minus T s. So, dA is du minus T ds minus S dt, and what is du minus T ds? It is nothing but du minus dq, which is dw, which is minus P dV minus S dt. Now, you just compare and you get minus S dt minus P dV. So, therefore, we got del A by del T at a constant V and N as minus S, and del A by del V at a constant T and N as minus P. So, you see we are also getting the derivative of the fundamental equations as new quantities. These are all again equation of state. So, these are also equation of state. Any derivative of fundamental equation will be equation of states. Now, comes the last one of the thermodynamic potentials, which is G, which is T P and N. So, dG is del G by del T at a constant P and N dt. So, as you see that after the fundamental equation, we have not assumed anything. We know the first law of thermodynamics, which is du equal to dq plus dw. We know the second law of thermodynamics, which is dq reversible by T is ds. We know that. After that, everything else comes from naturally from just the manipulations of the derivatives. So, del G by del P at a constant T n dP. Now, what is G? G is H minus T s. So, dG is dH minus TdS minus S dt, and dH is nothing but H is U plus PV. So, it is du plus VdP plus PdV minus TdS minus S dt. Now, du plus PdV, now we have to see that like du is equal to TdS minus PdV, we know that from first law of thermodynamics. So, let me see. So, du minus TdS is minus PdV. So, this is nothing but minus PdV plus VdP plus PdV minus S dt. This cancels, giving us VdP minus S dt. So, minus S dt plus VdP. So, from here what we get, that del G by del T at a constant P and N is minus S, and del G by del P at a constant T and N gives us V. Now, we get several such relations of, like, now we can get entropy by now several different ways. We can get entropy from Gibbs free energy, we can get entropy from Helmholtz free energy, like here. We can get entropy also from other thermodynamic potentials as well, and many different ways. Okay. So, all these relations of thermodynamic potentials are there to help us measure a certain particular quantity and compare that with the desired ones. So, for example, we cannot measure entropy directly. So, therefore, we can measure the free energy change with respect to temperature. So, let us say we calculate the free energy, which can be calculated by calculating the binding constant. There are ways to do that, and if you do that at different temperature, from there, from the slope of that. So, from the slope of G with respect to T, let us say the plot is like this, we can get from the slope of that, we can get the expression of entropy, as you can see here. Minus of that slope will give us the information about entropy. So, that means now using some measurable quantities, we will be able to get something which is immeasurable, and that is the sole purpose of calculating and performing this several different thermodynamic relations.